Then let's start it. So I'm proud to introduce Joel Wenger from the company Drivetek from Switzerland. Drivetek, I think it's the longest JMAG client in Europe. So really a company which has a lot of experience with using JMAG. Joel, of course, when you have started using JMAG, you was not at the company. But at this time, I think you were at the Bern University of Applied Sciences, where you have studied electrical engineering, where you have been a researcher. And since, I think, 6 years now, or 5 years, you work at Drivetek. And your presentation is about high performance PMSM optimization technique using JMAG Designer. Welcome, Joel.
Thank you. Well, hello, everyone. It's a pleasure for me to talk to you today as your speaker representing Drivetek. And that was not planned to happen, but okay, I will just skip this slide because of the kind of introduction. And I promise I'll keep it short, just an introduction of what Drivetek actually does. And for those of you who don't know what we're doing, we're founded in 2002, and we're an engineering partner for drive applications. So that's mainly automotive, motorsports, but also industrial applications. We have strong competencies in electronics and software design, as well as mechanics and electrical machine engineering. One of our main products is supplying high-speed inverters, multi-level inverters for turbo compressor applications, just like fuel cells or other drive applications with very high frequency. Our core competencies are basically system engineering. We have a whole team which is dedicated to design the system, machine as well as inverter. And we have a team of electric machines where I'm part of, or like 70%. We also have a large, those are our two biggest teams, the hardware team for PCB and electronic circuit design, as well as the software development team, which currently is our biggest division. And I'm also part of this team. Okay, so what am I going to talk about today? Mainly, first of all, when designing high-speed, high-power density motors, what are the challenges, or what are the challenges we usually face during the design phase? And after that, I'd like to present the toolchain we use, and where we start the design, the semi-analytical models we use for in-the-loop optimization. And I prepared a quick demo to show you the optimization procedure we currently employ. So what are the challenges in high performance or high performance density motor designs? Number one, of course, is keeping losses and the operating temperatures low. Because as most of you know, I guess, increased operating temperature also result in increased losses and a reduction of permanent magnet flux. And this is a little bit of a vicious cycle, because to compensate the decrease in torque due to the reduction in permanent magnet flux, we have to increase the current. While increasing the current, we also increase the losses. And while increasing the losses, we increase the temperatures. So I'd like to proceed, but it doesn't seem to work now. I'll just use the arrows. So how can we break the cycle of of increasing operating temperatures and reducing permanent magnet loss or performance? It's either by applying more cooling or more efficient cooling, but usually we're limited with the cooling performance of our machine. Like, it's very compact, we have a limited surface area, so that may not be feasible. The other thing we can do is increase motor efficiency, which is usually the path we strive for. Okay. So challenge number 2, high power paired with small volume and weight in machines usually results in very low inductance. And this has a multitude of effects. First of all, being the PWM current ripple, which can be very excessive and produce increased losses, which is not good. It results in increased short circuit currents, which depending on the application may be a problem. And it adds difficulties for the control system because of the low end. The high ripple currents measurement will be harder, and having a steady current vector will be more challenging. And also, if you want to reduce size and weight of the machine, this usually results in a machine with very high operating speeds, meaning increased iron losses, eddy current losses, and AC winding effects. We need higher PWM frequencies, of course, to be able to control the currents in the machine and the speeds. And also due to the high velocity, we usually have some compromises in the mechanical domain, just like the rotor binding, which needs to be strong enough so the machine doesn't fail during operation. And also, this usually results in limited fault tolerance. Something we found during the past few years is, do we want to design the best machine or do we want to design the best system? If we optimize the motor in isolation, usually this results in excessively high current requirements, as well as excessively high electric frequencies, because we don't need to consider the inverter or the system around it. And also, it usually results in even lower inductances. This may result in a very good machine performance when viewed in isolation, but very poor system performance if you consider additional components such as the inverter, the battery, the gearbox, and so on. So what we usually strive for is for co-optimization of the inverter as well as the electric machine, which are our two core competencies. We can include also models from the battery or the gearbox, but those two components we're kind of specialists for, and that's why we focus on the co-design, or at least considering the effects of one to another. Okay, an optimization is always something which at the base seems pretty straightforward, and it gets complex pretty fast. So before starting an optimization, what do we need to know? Mainly, those are the operation parameters of the machine, so the limitations or what the machine must be capable of, as well as the objective functions. This can actually be as simple as just having a multitude of objective functions which are weighted and summed up. Because what we want to really have is we want to optimize for one single target value. If you have a multi-domain problem, usually it's very hard to just find a good compromise. Of course, it's possible, and you also know optimization theory. There's something called the Pareto curve, but without knowing the parameter weights, it's very difficult to determine an optimum. So those parameter weights and knowing the objective function is not really necessary when we deal with a simple, straightforward optimization problem. It's absolutely necessary, though, if you're dealing with a multi-objective, multi-parameter optimization problem, because if you don't know our target functions, we can't really do an optimization. And hence, the target weights must be known beforehand. Okay, so starting a new design is always tricky. It's always exciting as well, right? We have lots of design space, like what's the best topology we're going to use, what's the operating temperatures we can expect, or the cooling performance, what dimensions can we use, or what mechanical and thermal limitations do we have. And sadly, or oftentimes, some of those questions can only be answered after the optimization. So this results in a little bit of an iterative process. We have a starting set point, and we go into our optimization. If you have found a design which seems to be optimal for your current boundaries and current constraints, we do detailed evaluation in the mechanical domain, thermal domain, as well as of course, the electromagnetic domain, and we compile those results. After compiling those results, we can determine, is the optimization converged, or do we need another iteration? And usually this process is, as mentioned, very iterative and quite tedious. So it makes sense to automate as much of this process as possible, so we don't lose time during the process. And also, it's very important to set a reasonable starting set point. Otherwise, this iteration loop will take forever. Okay, so how do we at Drivetek evaluate machine performance, especially during a starting phase or during optimization? So calculating individual load points is fine, and depending on the duty cycle of the application, that's all right. But usually we're more interested in the broad spectrum or an efficiency map of the operating conditions of the machine, and therefore we use a semi-analytical model, which we can extract using JMAG Designer. So first of all, we need to set the geometry in JMAG. This is your standard modeling phase where you use the geometry editor and set a baseline design. Afterwards, we calculate the coil flux linkages, where we actually employ a DQ current grid for a static analysis, and we extract those parameters from JMAG. After we extracted those parameters from JMAG, we start building our analytical models, and that's also where the know-how and the IP is located. And from these analytical models, we can extract machine behavior, like those graphs you see right here. They're calculated using this method. The whole time, or the whole process time to get those figures is around 2 minutes for a standard machine, which is way faster than just calculating a multitude of individual load points. Okay. Once we have the analytical models, we can evaluate those load points, or several load points, or even also a load profile with a few hundred load points, and refeed the result of that into the simulation. Additionally, especially during concept phase and during calibration, this is an important step, but it is optional to calibrate the model. We can refeed the currents and the parameters we found during analytical modeling into JMAG and validate the iron loss calculation, as well as the saturation. Okay, but usually, especially for during optimization, we omit just this final step, the validation, and we just feed back the results from the analytical model into the optimization loop. Okay, I prepared a little bit of a slide how this optimization procedure actually looks like. I'll try again with that because it's a little bit tedious. So first of all, we have the parameter settings within JMAG Designer. This is defining our basic dimensions after selecting a suitable topology. We afterwards run the calculations in JMAG Designer, and we export the results we need. So First of all, of course, we need to know the dimensions for our analytical model. That's we extract directly from the case. And we also extract coil flux linkage and as well as currents for the DQ grid. Additionally to that, we extract the stator B field as well as the B field in the slots. And those quantities are used for our analytical models. So first of all, we can calculate static parameters like DC resistance, weight, rotational inertia, and so on. We can create a DQ model from our fluxes and currents. We can create an iron loss model from the stator B field, and we can create the AC loss model from the slot B field. So that's quite a lot of analytical modeling, but can all be automated using Python. The DQ model, the iron loss model, as well as the AC loss model can be compiled into one single analytical model and combined with a, I don't think that's supposed to happen. Yeah, okay, I'll advance like that. Okay. Yes, so these analytical models can be combined with a multitude of other models, just like the inverter, can also be the battery or the gearbox, and compiled into one single big model within Python. And this model is then used to calculate the performance of those load points. This is also usually done using Python, and the output of that is our target value. So those are the weighted losses, weighted machine weight, weighted rotational inertia, and so on. And we can feed back those results or the result of this analysis back into the optimization algorithm and reiterate. So this process shown right here, this is the in-the-loop optimization we employ, and this procedure is fully automated. So once the study is set up, we can run the algorithm, and ideally, the output of the optimization is the best compromise of our target values. So for further demonstration, prepare the demo project just to show you what this actually looks like. We'll consider a machine with 150 Newton meters of torque, 200 kilowatts, regular high voltage DC link system, and also quite high power density. So also for this demo, I just set 4 different load points. Doesn't really matter. It could be hundreds of load points. We can evaluate within seconds using the analytical modeling approach. But it also works, of course, with 4 load points. And just for you to know, the design may look awful. That's because it doesn't represent an actual design. Okay, so as mentioned before, setting the initial design requires experience, or it requires a lot of time, one of both. After we did our manual iterations, finding a suitable starting point, maybe together with our systems engineer and our mechanical engineer, we determined the following baseline is good to go, and we start the optimization procedure. Are those dimensions we set initially already optimal? Most probably not. So how do we determine parameter ranges for our optimization? Usually this is done, or at least we do it in the following order, that we identify the most important parameters, like some radius inside the slot may not have the same impact on our final design, like the stator outside diameter. So in that, we identify the most important ones, and we employ a sweep of those parameters. Like at this stage, it can be pretty coarse, but it should cover the whole design range we want to cover. We can run all the studies, shown the process before, and we can evaluate the results of this parameter study. On the plot to your right, I know it's a bit hard to read, maybe focus, but of course, there are a multitude of results to consider. And our job as a designer is now to evaluate what parameter ranges do make sense, or what do we want to set. So ideally, after having analyzed this study, we have determined the optimal parameter range. How do we do that? So first of all, we can just look at the numeric results, or we can employ statistics to display the normalized correlation values. So here shown are just parameter correlations for losses and the resulting impact for 3 parameters, but this can be done for every single one. And this helps us to determine a suitable parameter range. Maybe it's also interesting to look at the statistic distribution of the losses for different load points or different load profiles. Just like shown here, for different load points, sometimes this varies from 20% to 100% copper losses in a single point. So this is also a good indicator if our search is maybe a bit too narrow or a bit too broad. Just an additional note, up until this point, for the demo project, we didn't consider PWM current ripple, but to be honest, usually it has a very, very high impact on our final design. So if you just look at the results of the of the study without the current ripple, we would determine design number 1 to be the best of those 6 selected designs. If we now include the PWM current ripple in the analysis, this changes. So for this study, the difference isn't too big, but especially if you misset the number of turns and hence the inductance, this can really throw off your whole design. So maybe at this stage, at latest, it's important to consider the effects of your inverter or of your PWM frequency on the machine. So we have had our initial set point, and we went from this to this. So basically not too bad. We said we were within the range. However, we did misspecify the initial number of turns. Okay, so far we have determined our objective function parameters, so the target weights. We have set the machine topology, and we've seen that it may be optimal or suiting our application, and we have selected a suitable parameter range. So at this point, we can actually start using the optimization loop. And yeah, this is I run this optimization for the demo project for all parameters we want to specify and we want to optimize, and the result is shown also to your right. At this point, the correlations may be interesting or may be of interest to you, but most certainly you're just looking for the optimal design, which can be filtered out of the impact. So once again, we went from our baseline design to our fully optimized design, where we adjusted every single parameter we have or we can vary. And even though the basic dimensions aren't too bad or aren't too far off, we can see a definite and quite significant change in machine characteristics. Also, if you look at the actual performance, we can see our first step with adjusting the parameters, and especially the number of turns, has had a very large impact on our overall machine performance. And also the optimization was able to get a few more percent out of the current restrictions and boundaries. So how could we potentially increase the efficiency or the precision of the optimization procedure? This would, for one, of course, be considering the effect of the AC ripple or the PWM ripple during the optimization loop, which is possible, but it increases runtime quite significantly. We could also run the same setup in 3D to have to include magnet losses, even for segmented magnets. And we also could include the winding heads for our inductance calculations. But once again, this increases runtime quite significantly. And finally, of course, that would be nice to have is in the loop thermal simulation, where we can penalize the losses or the additional loss due to the higher temperatures accordingly. And this would allow us to even further predict machine performance more accurately during the optimization process. But unfortunately, this is it's pretty complicated to extract model parameters for such an in-the-loop design, and we don't have the capability at the moment. And it also increases model complexity and once again the simulation runtime. So we can see those three improvements have something in common. It just takes longer for the optimization to converge. And depending on the application and time frame, that this might not be a problem. But if we start the design and like in a month's timeline, we need to have a base design, this might be suboptimal. Okay. That's pretty much everything I have to say. Thank you for your attention, and I'm curious for your questions.
Yeah. Thank you very much for your presentation. I suppose you have some questions. Who would like to start?
Thank you very much. Interesting presentation. I have a very simple question. I think you said that we need to determine weight of the to the objective function before. Is it possible because the sensitivity is unknown? So I think it's quite difficult to determine beforehand.
Yeah, well, usually we're in close contact with our clients and our system engineering department for this reason, to determine how the load points we're gonna evaluate are weighted. And before it isn't fully determined what the objective parameters are or the optimization constraints, we usually don't start an in-depth machine optimization. Maybe we do some kind of parametric study to evaluate approximate performance for, again, iterating with the system design. But once we start optimizing and using really advanced modeling techniques, we usually need to know what the target weights are.
Okay, I understand. Thank you. Reasonable. Yes.
Okay, thank you. Other questions?
Yeah, for the optimization, do you use any cloud-based environment or HPC, or it can be run on your workstation as well?
Yeah, it is all run on the workstation. So unfortunately, we don't have cloud-based analysis. That's also why we employ strategic analytical modeling instead of just brute force calculations on the cloud.
Okay, some more questions? Yes.
Two questions. One is how many geometry parameter in this demo model?
Oh, I need to count, but I think it's around 12 to 15.
Okay. And the second question is, last you mentioned about the time. Mm-hmm. So can I ask your accepted the time for the optimization?
I'd like to have an iteration finished within 3 days.
3 days.
Yeah.
Okay.
So running from the parametric modeling or parameter range search to the final optimization, I'd like to have to be complete that everything in 3 days.
So from the scratch to end, you
Yeah.
can wait 3 days.
Mhm.
Thank you.
And all that's important because usually you need to iterate again with mechanical department and thermal analysis. So we don't want to spend too much time for the optimization.
Thank you.
Okay, so we had 4 questions. Okay, perfect. Then thank you very much again for your presentation, for your questions and the discussion.
Thank you.